Okay, thanks very much for having me. So I'll just jump right in. Um, this talk is really interested in how we can understand what shapes language. So why is it that languages look the way they do? And there's lots of potential explanations, and sort of different approaches to linguistics tend to sort of focus on some subset of these. So for example, there's a number of prominent theories that start with the sort of foundational assumption that there are forces shaping language that are specific to our linguistic system. So for example, there's a kind of constrained language faculty, which allows us to generate some types of languages and not others. So that's one potential force that can shape why languages look the way they do. There's also the idea out there that the cognitive system more generally, so not the linguistic system in particular, but cognition shapes language through kind of domain general biases that might, for example, make some types of languages more common than others. And then, of course, there are a number of sort of more cognition external features that we know shape language. So, for example, some languages might be quite similar to one another because they share a common lineage. It might be that certain types of languages look more common than others through accidents of history, and even things like geography or climate have been claimed to shape human language. So we've got this sort of host of different types of explanations, and we might want to know in any particular case sort of which one of these is playing a role. And in terms of like if you're coming from linguistics, there are some kind of more traditional data sources that people have used to try to suss this out. So probably the most common one is typological samples. So the map that you see here is from the World Atlas of Language Structures Online, and each dot on the map is a language. So you might look at a typological sample like that and notice that the gray dots outnumber the green dots. And so you might come up with a theory for why that is. There are other types of traditional data sources like grammars, fieldwork, introspection. And these sources of data have produced a number of very interesting observations about what language looks like, and also a number of theories for explaining why languages look the way they do. But they also have some pretty serious limitations. So for example, typological samples are often based on very sparse data. So maybe in the best case, you're talking about a couple of hundred languages, and that's really not very many in the scheme of things. In addition to that, typological data on their own can't really tell you what the explanation for themselves is, right? It doesn't really work that way. So as we saw on the previous slide, there's lots of potential explanations for why, say, this map looks the way it does, why there are more gray dots than green dots. And on its own, it's hard to figure that out just based on the typology. And what that means is that it's very difficult to actually make claims about a causal link between, say, constraints of the linguistic system or domain general cognitive biases and any particular typological asymmetry like the one you see here. So what I'm going to tell you about today is some new sources of data that allow us to maybe push a little bit further in establishing that kind of causal link. And I think the sources of data are generally experimental. So there's lots of work in psycholinguistics using experiments, but I'm going to tell you today about a sort of different specific type of experimental paradigm that I'll call artificial language learning. Sometimes it's called artificial grammar learning. And artificial language learning has been around for a long time in developmental psychology, and it's used somewhat more in phonology, but it hasn't really gained too much traction in syntax and semantics. So I'm going to tell you about how we can use those these types of experiments in a couple of different domains. In particular, I'm going to focus on two case studies here. They might seem quite different from one another in a way they are. So the first one is person systems, and the second one is noun phrase word order, but they have a couple of interesting things in common. So for one, in both of these domains, we have a number of alternative theories that typically focus on sort of specific to the linguistic system constraints that are often taken to be sort of hard and fast constraints. So there's a subset of possible languages, and then another subset of languages that are sort of ruled out by the system. And they're also driven by very sparse typological data. And so these are good domains in which to expand the base of our empirical evidence that we have using artificial language learning. And I'll mainly be talking here about evidence from these paradigms, from artificial language learning paradigms, for soft biases rather than hard constraints. So the idea being that the systems that we're going to teach learners, so they'll be artificial languages, but they'll be constructed to allow us to test specific hypotheses. And they'll generally be showing us things like some patterns are easier to learn than others, rather than some things are impossible. Okay, so I'm going to jump right into to talking about person systems. So person systems are generally a way of categorizing speech events based on their participants. So for example, pronominal paradigms are a good example of an instantiation of the person space. And we can typically identify the speaker, the addressee, and others. So the others are not necessarily directly involved in the conversation. And these are sometimes referred to as first, second, and third. Sometimes it's I, you, and O. I'm going to use first, second, and third here. And if we look across languages, there's evidence for a fourth person category that includes both the speaker and the addressee. So this is not a number distinction. This is often called the inclusive person. And that can be contrasted with the exclusive person that includes the speaker and others, but not the addressee. And then the plural of the inclusive person includes the speaker, the addressee, and others. So that's the person space, and you can see that it interacts with number. Okay, so we have this this 8-cell person space if you consider the 4 persons and, for example, a number distinction between what I'm calling minimal and non-minimal. You don't really need to worry about that, but it's kind of similar to singular and plural. And the question immediately arises, like, how are these categories lexicalized in languages? So if we have an 8-cell space, then in principle, we can get 4,140 possible partitions of this space. So meaning that there are different ways in which languages can map forms to meanings, so say pronouns to these individual cells in the space, but only a small minority of these possible partitions of the space are actually attested. The exact number of them depends on how you count, and people do that different ways. But here's one representation of the different types of person partitions that we see across languages. And what you see here is the way the cells are colored indicates whether 2 meanings share a form. So in other words, the colors indicate homophony patterns within a language. So for example, if we look at the English paradigm here, we can see that there are several cells that have a different meaning but share the same form. So English doesn't distinguish inclusive and exclusive, so you get a nice teal chunk there for all of those forms that are expressed by the same meaning, by the same form. And then we also have homophony in the second person, so we just say you, regardless of whether it's singular or plural. Here's an example of a similar language, but that doesn't have this funny homophony pattern in the second person, that's Spanish. Then you can see some systems like Mandarin that have the inclusive-exclusive distinction. And finally, a language like Ilocano, which has a distinct form for all of these 8 cells. So different possible partitions based on these different homophony patterns. And what we're going to be talking about today is asymmetries among homophony patterns that we see in typology. So if we look across, for example, pronoun systems in the world's languages, we can see that not all patterns of homophony are equally frequent. So for example, here, the different rows are homophony between the first and the third person, homophony between the second and the third person, and homophony between the first and second person. And you can immediately see that it's very rare for languages to have homophony in the singular, but you do get some homophony patterns in the plural. And if we sort of add these up, we can see that homophony between the second and the third person is the most common, then homophony between the first and the second person, and then homophony between the first and the third person. But you will have also noticed that this table doesn't have very many languages in it. So there's a very sparse typological sample. All right, and now I'm going to talk you through a couple of different theories of person that make predictions about how common these different homophony patterns might be. So theories of person space are generally set up to constrain the set of possible partitions humans can represent. So that's what I meant by hard constraints before. So these theories will generate some partitions and not other partitions. And they're also designed to explain the prevalence of certain partition features. So for example, certain patterns of homophony. So perhaps the most straightforward such theory is usually referred to as the binary features theory. So in this theory, each of the four persons is represented by two binary features, plus minus speaker and plus minus hearer. And we can think about what these features have to say about homophony patterns. So if we generally consider homophony patterns to be just determined by some kind of similarity, here we can think that similarity is determined by shared feature values. So for example, the second and the third person share the feature minus speaker. The first and the third person share the feature minus hearer. And the first and the second person don't have any overlap in their specific feature values. So if we map that back onto patterns of homophony, this theory would predict, for example, that second and third homophony and first and third homophony should be equally likely, but first and second person homophony should not happen. Here's a slightly different theory. It generates the same four-person system, but it looks to sort of codify the relations between the different persons using feature geometry. So in this theory, you can see that there is something in common between the speaker and the addressee. They use this participant node, whereas third person in this theory is actually a default person, so it doesn't use the participant node at all. So again, coming back to our homophony patterns, this would predict that you should see homophony between the first and the second since they share this participant node, but not between the first and the third and or the second and the third. One more theory. So this theory, again, it will represent the same four person categories, but it treats features as functions. So what happens is it takes the set of event participants and it applies a function to those to get a subset. So for example, if you apply the proximate function one time, then that will get you the speaker and the addressee. And if you apply it another time, it will get you the most proximate of that set, which will be the first person. So here similarity is determined by shared function composition. And first and second person share this function proximal, and second and third person share a function distal. So this would predict that you should get homophony between both the first and the second and the third, but not between the first and the third. Okay, so we have our typology, albeit sparse, and we have these three different theories. All of them make different predictions about what homophony patterns might be more common, or in particular, what homophony patterns might be more natural for humans. So that's the way we should probably think about it. Now I'm going to set aside the binary features account right now because it's generally recognized to not be quite as good, and it makes some sort of unlikely predictions about homophony patterns in this domain. So I'll focus on feature geometry and shared features. But the idea is that it's not really clear where to go from here. So we have these two theories. They don't exactly match the typology, but the typology is very sparse. So how do we actually go about adjudicating between these theories? And as I said, these are, after all, hypotheses about how humans represent the person space. So they should be reflected in behavioral data. And this is where experimental paradigms like artificial language learning can come in and help us out. So I'm going to turn to an artificial language learning experiment now. This experiment uses a particular type of design that I call the extrapolation paradigm. And the way this design works is that we train participants on input that's purposefully ambiguous. So in this case, we'll train them on part of a person partition, and we'll hold out a critical part of that partition. And then we'll try to get at what paradigm participants or what partition participants are actually inferring based on this ambiguous input. So for example, we might train them on a person paradigm that distinguishes all the forms in the singular. And then we might train them on a subset of the forms in the plural. So we might train them that first person plural and second person plural have two distinct forms, but we never show them the third person plural. And then they're forced to use one of those two forms to express that third person plural at test. So what that means is that in principle, they could either use the second person plural form to express the third person plural, in which case they will have derived homophony between second and third, Or they can use the first person plural form to express the third person plural, in which case they will have derived first third homophony. And we can do that for a number of different ambiguous paradigms. So here's an ambiguous paradigm where we teach them that the first person plural and the third person plural are distinct, but we hold out the second, in which case they could infer either second third homophony or first second homophony. And finally, we can teach them a paradigm in which second and third person plural are distinct, but we hold out the first person plural, and then they can either infer first third homophony or first second homophony. Sorry, I can only see part of my slide, so I hope I set that in the right order. Okay, so that's how this experiment works. And then hopefully you will have got the sense that each of the different theories we talked about, as well as the typology, kind of make different predictions about what the pattern of results should be across these different scenarios. So for example, based on the typology, the expectation is that whenever people can infer homophony between second and third person, that's what they should do. And when they can't infer homophony between the second and third person, then they should instead infer homophony between the first and the second person. By contrast, the feature geometry account predicts that it's actually first-second homophony that should be the most likely to arise. So whenever that's a possible pattern of inference, that's what people should go for. By contrast, if they can't do that pattern of homophony, they should be equivocal between the other two. For the shared features account, the prediction is that whenever people can produce second, third homophony or first, second homophony, they should do so. When they can't do either of those, or when one of those is pitted against first, third homophony, it should always win out. So people should not do first, third homophony. Okay, so different patterns of predictions. Now I'm going to show you what people actually have to do in the experiment because it's probably not intuitively obvious. In fact, this is kind of a complex setup. So what we do is introduce people to a family, the Smiths. These are the people who are going to be event participants. You have the three sisters at the bottom, Anne, Mary, and Little Sue. Anne and Mary are always the active event participants, so they're the ones speaking. And Little Sue is just sort of there, but she's not an immediate event participant, so she never does the speaking. And we tell them a little backstory. So we tell them that it's Anne's birthday, and Mary and Little Sue found a special hat for her in an antique shop. And if you wear the hat, you can see the future. But unfortunately, not only do you see the future, but you start speaking a mysterious ancestral language. So we tell them that Mary is going to start asking Anne some questions about events in the future life of the family, like who will be fat? Not a very nice question, but we just came up with random questions. And then Anne is going to answer the question using one word in the ancestral language. Okay, and the idea of the task is that they need to find out what these words mean. Okay, so here's an example training trial. So here you see Mary asking who will be fat, and you see Anne producing the form lam. And what we do is highlight the event participants who correspond to this meaning. So here this would be the first person plural meaning. Here's a different form, kip, that would have the second person plural meaning. And then at test, we would show them a meaning they've never heard before during training. So here that would be the third person plural, so something like this. So we have different sets of participants that can instantiate the third person plural, but we sort of go randomly between them. And the idea here is that if the participant chooses kip, then they're using the second person plural form for the third person plural. If they choose lam, then they're using the first person plural form for the third person plural. Okay, so that's how the experiment works. Hopefully that's clear. All right, and then we can take a look at the results one by one. So first, the system where we teach people that first and second are distinct from one another and ask them to make a guess about the third. So here, both the typology and the shared features account predict that people should go with second, third homophony. The feature geometry account predicts that people should be equivocal between the two. So here I'm showing you the proportion of yellow choices. What does that mean? Well, it just is going to correspond to whichever of the persons is yellow. So here, this is the second person plural form. Okay, so first I'll show you the two forms they were trained on. So first and second person plural, because they'd better get those right. And they generally do. So you can see that they pick the yellow form where it's appropriate, and they don't pick it where they have learned a different form. And then the question is, what form do they pick for the third person plural? And what you see is that they generally pick the yellow form. So what that means is that they're inferring second, third homophony. Okay, so next condition is where we teach them that the first and the third are distinct from one another. Here, the typology again predicts that they should go with second, third homophony. The shared features account here predicts that they should be equivocal between the two, and the feature geometry account predicts that they should actually go with first, second homophony. So again, you can see that for the trained forms, people behave as expected, and then the question is, what do they do for the held out form? And here again, they go with the third person form, which means that they're inferring second, third homophony. All right, and finally, the condition where we teach them that the second person plural and the third person plural are distinct, and they have to produce one of those forms for the first person plural. Here, all three predict that participants should go for the first, second homophony pattern. So again, on the trained forms, people are producing the forms that they should, but actually they're equivocal when it comes to what to produce for the first person plural. So you have some people who are consistently producing second, third homophony, first, second homophony, some people who are consistently producing first, third homophony, and some people who just don't know what to do. Okay, so setting these results back up against our typology and our two accounts, what you can see is that our learning results don't match either of the two theoretical accounts. They're actually a bit closer to the typology. So if we look back at the typological numbers, it's definitely the case that second, third homophony is the most common. Both first and second and first and third homophony are pretty rare. Okay. So to summarize, it's definitely the case that not all homophony patterns are created equal. They're not all treated equally by learners. In particular, the second, third homophony pattern is consistently inferred by participants, by which we can conclude that this is a kind of natural homophony pattern for people to do. By contrast, first and third homophony and first and second homophony clearly aren't. Now, this mirrors the typology, however sparse it may be, but it's a challenge for current theories of person. So as I described to you, neither of these two theories make this prediction. So in particular, this confirms that there's a shared feature that second and third have with one another that's not shared by the first person. And further, it suggests that even though it's sort of intuitively the case that first and second person are both participants, and so they do share something in that way, there's a clear asymmetry between them in people's minds. Okay, so this was just one experiment, or one set of experiments in a larger set of experiments that we've been doing on person systems, because these theories make a number of other predictions about different types of homophony patterns that we can test using this kind of paradigm. In the next steps, so you've noticed here that we focused very narrowly on the role of features in determining what kinds of homophony patterns people do, but even our results suggest that maybe features are not the only thing that's going on, so we're interested in looking at other types of biases. So for example, it may be that there's a kind of egocentrism bias that causes people to want to maintain a distinction between first person and the other persons. It's also very possible that there are effects of what's sometimes called communicative efficiency. So it might be that when we're actually speaking, there are some kinds of asymmetries we often need to distinguish. So there are some types of categories we often need to distinguish between, and other types of categories we need to do so less often. So there are other types of biases besides shared features that can actually be coming into play in these systems. Okay, so that is it for person. If there's no immediate clarification type questions, then I will move on to word order. Yeah? Okay, so noun phrase word order. In this part of the talk, I'm going to be discussing how people order nouns and 3 different types of nominal modifiers. So in particular, demonstratives like this, that, these, those, number words, and adjectives. So in English, we use the order demonstrative, numeral, adjective, noun, but different languages use different orders of these elements. So for example, Thai uses the mirror order of English, noun, adjective, numeral, demonstrative. And you can see some other different orders here in French, Indonesian, and Kitaraka Bantu language. So there are 4 words here, and so that gives us in principle 24 different orders. And so we can have a look at a decently large typological sample, bigger than the one I showed you before for a person, and see, well, what does it look like in terms of these 24 possible orders? So you can see that some of them we have examples of, we've found them in languages, some of them we haven't. The Thai order, so that's the mirror of English, noun, adjective, numeral, demonstrative is the most common, then English, then some others. You can see it kind of, the distribution tails off pretty quickly. All right. So I'm going to tell you about a kind of generic theory of noun phrase word order. That's sort of representative of how these theories generally work, coming from generative linguistics. So these theories of noun phrase word order generally start from the idea that there's a sort of underlying structure in this domain. And I represented the structure in terms of a mobile. That's because if I showed you a syntactic tree, you might think I was referring to linear order, and I'm not. So the idea behind this structure is to represent sort of constituency relationships rather than linear order. So in particular, the idea is that in this domain, you have a constituent that's consists of just the noun and the adjective. And then if you want to add a numeral, it's going to add to that constituent to form a larger constituent. And then in turn, if you want to add a demonstrative, it's going to add another layer of structure and a bigger constituent on top of the other 2. Okay, so theories of noun phrase word order tend to start from that as a basis. And then they might add some sort of hard and fast constraints that determine what kind of movements you can do within that space. So can you take the noun and move it all the way up to the top of that structure or whatever? So here's one example, Ebels and Nealman, 2012. So they start with this underlying structure, and they first derive 8 possible linearizations of that structure. So if you take that structure and you just make a decision for each constituent of how you're going to order the elements in it relative to one another, you get these 8 orders. So if you've got the adjective and the noun, you can either order them in that way, or noun adjective. Once you add the numeral in, you can either order the numeral on the right side of that or the left side, and so on. So that's those 8 orders. And then they have a series of constraints on movement. So you can take those orders and move things around, but you would only do that in certain ways. In particular, you can derive 6 additional orders that way, but that's it. So you have 8 plus 6, 14 orders, and the rest are impossible. So they cannot be derived according to the system. All right, so let's look back at the data. So I've grayed out the languages that this theory predicts should be impossible. And you'll notice right away that some of them are in fact attested. So in principle, one could futz around with those theories and try to make it so that there's a line drawn right here between the languages that never occur and the ones that do. But I would argue that this is potentially problematic because it does nothing to explain, for example, why Thai is very common, and a language like Kitaraka, that pattern, noun, demonstrative, numeral, adjective, is very rare. And further, the more we look, the more languages we find. So for example, there's recently been some languages that have been claimed to have one of these orders that's unattested, that was unattested previously. So instead, we're going to focus on the idea that we should account for the shape of the distribution rather than just the distinction between what occurs and what doesn't. And in fact, if we go back to just this hypothesized underlying structure, the underlying structure can actually do a pretty good job of explaining potentially what these frequency differences are in terms of which types of patterns are very common. So remember, I told you that this underlying structure captures the idea that there's a kind of constituency relationship that includes just the noun and the adjective. Then you tack on the number to make a larger subconstituent than the demonstrative. And this generated these 8 orders. And these 8 orders are also the ones that are highlighted in green on the plot below, and you can see that they're amongst the most common orders. And it doesn't really matter what typological sample you get, you'll always get these 8 orders being amongst the most common. So you can do various things to control for the relationships between languages and such, but it always comes out that way. Okay, and yet, oh, sorry. And I typically call this the homomorphism bias. So the idea is that you've got this underlying structure, and in principle, you have a way of transparently mapping that to linear order. So all of these, all of these patterns here sort of just transparently reflect that underlying structure. You can read them all off of that mobile. So that's the idea of homomorphism. But as before, you can't really just take typology at its word and assume, okay, well, the typology shows us that there is such a bias, because there's lots of reasons why the typological distribution might look the way it does, and we really need more evidence in order to establish a causal link between the typology and this kind of bias. So again, we're going to turn to artificial language learning to do that. And actually, we're going to use a very similar type of artificial language design, so the extrapolation paradigm again. In this case, again, we're going to give participants ambiguous input, but here we're going to be asking, given that ambiguous input, what word order do participants infer? So for example, here, we might train them on a language that has post-nominal demonstratives and post-nominal adjectives. So we're going to train them on how nouns are ordered with respect to single modifiers. And then at test, we're going to ask them to produce phrases that have multiple modifiers that they won't have seen during training. So for example, if they're trained that demonstrative and adjective come after the noun, they might be tested on the relative order of demonstrative and adjective. And they could produce it noun, demonstrative, adjective, or they could produce it noun, adjective, demonstrative. Similarly, we could train them that both demonstratives and numerals on their own come after nouns, and they will have to infer, well, what is the relative order of demonstrative and numeral? And finally, we can train them on numerals and adjectives and ask what's the relative order of those elements that they infer. Okay. So if there is in fact a homomorphism preference, this makes clear predictions about which ordering patterns participants should infer on the basis of this ambiguous data. So in particular, they should always keep the adjective closest to the noun. The numeral should be next, and then the demonstrative should always be furthest away from the noun. So that gives you noun, adjective, demonstrative order, noun, numeral, demonstrative order, or noun, adjective, demonstrative order. We can also make a different prediction based on the population of participants that we're testing. So here we're going to be testing English speakers, and English has a particular surface order of these elements, namely demonstrative, numeral, adjective. So in principle, people could just use the surface order of modifiers in their language to infer what order it should be. And in that case, the predictions are always the opposite of the homomorphism predictions. So people should infer noun, demonstrative, adjective, because demonstrative adjective is the order of those elements in English. Okay, so the setup here is simpler than the one before. We don't have to introduce people to a crazy family. We just tell them that they're learning a small part of a new language with a made up name. We make up some details about that language so that people take the task seriously. And then they're told they're going to do a short series of learning and testing tasks. So here's what the training might look like here. So you can see that this experiment was designed for children. That's why it has this little cartoon look. But in particular, you might see, participants might see a feather that's red, and they would hear an utterance like "aye taka." And across the experiment, they should learn that "aye" is the word for feather and "taka" is the word for red. So in this language, adjectives come after the noun. They might also see trials like this, where the girl, the speaker, is pointing to one of two elements. One is closer, one is further. And she might say something like "eye hono," and they need to learn that, again, "eye" is the word for feather, and "hono" is the word for a distal demonstrative. So in this language, demonstratives follow nouns. Okay, what they don't see are trials like this, where you need to use both an adjective and a demonstrative. So we wait until testing to show them these trials, and then they have to actually produce a phrase using the words that they've learned in the language to convey this meaning. And the idea is that in principle, they could either produce noun demonstrative adjective or noun adjective demonstrative. All right, so here I'm showing you the proportion of participants' productions that follow the predictions of homomorphism or not. So in the first case, do they produce noun, adjective, demonstrative? And the answer is yes, they do. They have a very strong preference for doing so. Secondly, when we train them on demonstratives and numerals, do they produce noun, numeral, demonstrative? Again, yes, they do. And then when we train them on numerals and adjectives, do they produce noun, adjective, numeral? And they do again. So there is a difference here. So there's a slightly weaker preference for numerals and adjectives. So you can ask me about that if you want in the question period. But what you see here is across the board, they have a pretty strong bias for going for the homomorphic order. So that gives us evidence that English speakers are biased in favor of these homomorphic orders. So they're more likely to infer orders where you get the adjective closest to the noun and the demonstrative furthest away and the numeral in between. Now, if you are a skeptic, and you should be, you might be thinking, well, English is a homomorphic language, right? So maybe it's just the case that participants here, rather than using information coming from the surface properties of English, they're sort of using their knowledge about the constituency structure in English to do this task. So we've got some ongoing work which is unfortunately very much not happening right now because of the pandemic, but we're looking at speakers of a non-homomorphic language. So these languages are necessarily rare. It's not easy to find monolingual speakers of these languages, but we're currently working with speakers of a Bantu language, Kitaraka, who have the order noun, demonstrative, numeral, adjective. So that order is not homomorphic. It does not have the adjective closest to the noun, the demonstrative furthest away. It's the opposite. And so we'll see whether these participants also have a bias when they learn a new language in favor of homomorphic ordering. So that will be a much stronger test of this hypothesis. In the meantime, I'll show you a little bit of data from a very different kind of artificial language paradigm called the silent gesture paradigm. So in this paradigm, instead of training participants on a language or a subpart of a language and seeing what they do with that, instead, we bring participants in and we just ask them to spontaneously create a sort of little language using only their hands to convey meaning. This paradigm has been used a lot for work on basic word order. So how do we order subject, object, and verb? And it's generally been claimed that there's less evidence of influence from people's conventionalized spoken language on their behavior. So for example, English speakers often use SOV order in their gestures. So we're going to use this to see what people do for noun phrase word order. So here's what this looks like. So again, instead of giving people ambiguous input here, we just gave them no input at all, and we'll see what do they do. And you can see a participant here who's sitting in front of two mysterious black boxes. They're actually just iPads. What happens in the task is that they will see a picture appear on one of those iPads, and they have to provide a gesture for it. So here you should be able to see that we have sort of all the elements of meaning that we had in the noun phrase before. So we've got an object, it's a toothbrush. It's got a property, namely it's striped. There's a numerosity, there's 4 of them. And the iPads are doing the job of the demonstrative meaning. So there's one that's close to the speaker and one that's farther away from the speaker. Okay, so we can have a look at the kinds of gestures that people produce when they're confronted with this rather odd situation. I'll look again. So what you should be able to see is that she first indicates which iPad it's on, then the noun, then the fact that it's striped, then the numerosity. Let's have a look at another. So here, the object appears on the proximal iPad. It's spotted pencils, and there's 4 of them. So you've got pencil, spotted, for this, something like that. Okay, so if you were listening carefully to my little translations of their gestures, you will have noticed that those were isomorphic orders. So in the first case, you had noun, adjective, numeral, demonstrative. In the third case you see here, you had demonstrative, noun, adjective, numeral. I've given you another example of a gesture that's demonstrative, numeral, noun, adjective. So those are all different orders, but they're homomorphic orders, and none of them is English. So this is a general pattern of results that we get in these experiments. I can give you some more specific results in the question period if you want, but the overall take-home message is that here again, we see participants here actually spontaneously producing isomorphic orders. Okay, so that's some additional evidence that English speakers are biased in favor of homomorphic orders. So participants infer adjective closest to the noun, demonstrative furthest away when we train them on ambiguous data, and they also improvise these orders in gesture. Okay, so that's it for experiments. I've got one more thing I want to talk to you guys about before I end the talk, which is, where does this underlying structure come from? So I told you before that most generative theories of noun phrase word order sort of assume this underlying structure. And they typically talk about it in terms of constituent structure, but it's often treated as a kind of underlying syntax that people have innately. So it's often not explicit that this is thought of as something that's innate, but that's how it sort of is. And I want to suggest that instead, maybe this is about conceptual structure rather than syntactic structure, and that in fact, it might be that this is a kind of learned bit of information rather than innate. Okay, so I'll start by giving you a kind of intuition about why I think this is more about conceptual structure than syntactic structure. So if you look at objects in the world, it's easy to notice that they're very closely associated with their properties. So for example, fruit and wine are very closely associated with their color. We've got some other elements in the world, either naturally occurring or man-made, that are very closely associated with their texture. And you can easily find examples of, for example, animals that are very closely associated with, say, spots or striped. So those are properties that we typically convey with adjectives. By contrast, if you look at numerosities, it's harder to find objects that are very closely associated with their numerosity, but it's possible. So some things come in pairs, maybe some things come in kind of moderate numerosities or very large numerosities. So it's possible, but it's less likely. For demonstratives, so the kind of meaning that demonstratives give you is something like, you know, what is the location relative to the speaker, or other kinds of information like that that's relevant, that depends on the discourse. And those are kind of by their very nature not tied to specific objects. So you don't get objects that are closely associated with being far from the speaker. That's pretty uncommon. So the intuition, to summarize, is that objects and their properties are very closely associated with one another conceptually, whereas objects and their numerosities are less so. Nevertheless, objects and their numerosities are more closely associated to one another than objects and, say, their discourse status relative to the speaker. Okay, so how might we evaluate whether this intuition is actually true in the world? Well, ideally, we would get a giant corpus of objects in the world and we would quantify it, but we don't really have that kind of information yet, unfortunately. So instead, we're going to use corpus statistics as a proxy, the idea being that people talk about objects in the world. And to quantify this more precisely, we're going to use an information theoretic measure called pointwise mutual information. So here's the equation for pointwise mutual information. It's very simple. So in the numerator, you have the frequency of co-occurrence of two elements, say a noun and an adjective, or an object and property. In the denominator, you have then the frequency of those individual elements. And so two elements will have a high pointwise mutual information to the degree that the frequency with which they co-occur is higher than expected given their individual frequencies. Okay. So if we want to estimate the PMI of different types of modifiers and nouns in a corpus, what we do is we get all of the bigrams of nouns and modifiers and their frequencies. We actually discard the very low frequency pairs because they're known to sort of skew PMI values. We calculate the PMI for each of these pairs, and then we average that within modifier types. So we take all the noun adjective pairs and average their PMI, all the noun numeral pairs average their PMI, and all the noun demonstrative pairs and average their PMI. So the way we do this is that we allow some words to intervene. It doesn't have to be a contiguous string of bigrams. And we don't care about order. So it could be that the modifier comes before, it could be the modifier comes after. That's not part of this calculation. Okay, so here are the results from a large corpus of English, the Brown corpus. And what you can see here is that as we expected, as we predicted, the pointwise mutual information on average between adjectives and nouns that they modify is the highest, then numerals and nouns, and then demonstratives and nouns. So some examples of high PMI combinations would be something like alcoholic beverage, dense vegetation, 7 founders, which is something religious, I believe. And then low PMI combinations are things like that child or new fact or one program. So you can sort of pretty intuitively see that there's not something special about the connection between that and child. All right. So we obviously want to know that this is not something about a particular corpus or a particular language. So we can take this same calculation and do it across a number of different languages. And here are the results for that. Notice we also include all the English data from Childus, just to see whether this kind of information is actually present in the kind of speech that a child might hear when they're first learning about the conceptual relations between these things. And we can run a big regression model in all of this and see that across all of these languages, we get a robust difference between PMI for adjectives and nouns compared to numerals and nouns, compared to demonstratives and nouns. Okay, so what that tells us is that according to this particular information theoretic measure, nominal modifiers differ in their strength of association with nouns. So in particular, adjectives are very closely associated with nouns, numerals less so, and demonstratives even less so. And the idea is that you can, in principle, learn this by observing facts in the world. So recall, we sort of derived this information from a corpus, which is not ideal. We would rather derive it from objects in the world, but using corpus statistics as a proxy, it looks like in principle one could learn this kind of information easily. And the idea is that this information can then be used to build up an initial representation of conceptual structure in this domain, which can then be mapped to syntactic structure to derive these common linear orders. So this is a very preliminary work, and you can see that there's a number of gaps we have still to fill in, but this is the general idea about where this underlying structure might actually come from. Okay, so just to back up and give you a kind of general take-home message of the talk. So I started by saying that one of the major goals of linguistics is to build theories about what shapes human language, right? So why do we see the patterns we see across human languages? And we know there's a lot of different forces that can potentially shape typology. So there could be constraints on the linguistic system. There could be sort of domain general biases coming from cognition, like memory, perception. And we know there's a number of cognition external forces that also shape language. And the question is really, well, what is the sort of relative contribution of these different types of forces for any given feature of language that we want to explain? There's a number of traditional sources of data that have been used in the field of linguistics to try to answer these questions. For example, typological samples. And the two case studies I told you about today both deal with pretty sparse typological samples. So we've got a particularly sparse one for person systems, a little bit better for noun phrase word order, but still not great. And obviously these typological data alone, even though they're intriguing, don't tell us, whether they're the result of constraints on the linguistic system or cognition external forces. So they don't allow us to establish a good causal link. My main goal in this talk is really to show you that experimental methods like artificial language learning can allow us to make a more direct link between features of language typology and features of human behavior. So they don't necessarily tell us whether whether a particular bias is specific to the linguistic system or the cognitive system, but that's something we can sort of do as a next step. So I gave you one example of a case where we found a bias, and then we can sort of look further and ask then, well, what might the origin of this bias be? All right, and I'll just end by thanking my many collaborators on these projects and you for listening.
Okay, so